So this is the first lesson in the last part of the course, introducing logarithms. And eventually by the end of this chapter, in this section, anything we did with exponential equations that involved graphing to solve an equation, we'll be able to solve algebraically using logarithms. First, let's understand what a logarithm is. And a logarithm is the inverse of an exponential function. And I start with, an exponential function here, and this is y equals 2 to the power of x. Well, the inverse of that we call log base 2 of x. And it looks like that. That's how we write it. And literally what that means, log base 2 of x, means the inverse of 2 to the power of x. And so let's think what the graph would look like. We learned long ago that inverses in terms of graphs can be thought of as a reflection along the line of y equals x, or just by its equivalent, finding any point and replacing the inputs and the outputs, swapping your x and y's. And so, for example, instead of having a point right there at 0, 1, it's going to have a point at 1, 0. And if I do the same thing for the other points I have plotted, I quickly get these points here. And whereas a exponential function has a horizontal asymptote on the x-axis, a logarithmic function will have a vertical asymptote on the y-axis. And hopefully by now you can see the shape of this particular logarithmic function. And this again we write as log base 2 of x. And that base you see right there, that 2, corresponds with the base of the exponential function. And I'll draw the reflection line, y equals x. Notice how inverses keep coming up in this course. And again, a logarithm is the inverse of an exponential function. And so if we know, without even looking at the graph, we know that 2 to the power of x has a domain where x can be all real numbers. We've seen that from before, which means I know the range of a logarithmic function must be y, must belong to all real numbers. And again, without even looking at the graph, I know 2 to the power of x is a range of y is greater than 0. Therefore, I know the domain of this logarithmic function must be x is greater than or equal to 0. Now granted, log base 2 of x is just one type of logarithm, just like 2 to the power of x is just one type of exponential function. But once you understand one type of exponential function, we realize they're all fairly similar. Same thing for logarithms. All right, so let's generalize this, starting with exponential functions. And in general, there's two types of exponential functions. One where your base is greater than 1. And that's what we call exponential growth. It looks something like this. Has a y-intercept of 1 and a horizontal asymptote on the x-axis. Well, the corresponding logarithmic function, when you have a base of c that's bigger than 1, has a vertical asymptote. And is essentially what we just kind of sketched out. The x-intercept is 1, and it looks something like this. So again, that's essentially what we saw before. However, what if we have an exponential function where the base is between 0 and 1? Well, it has the same x-intercept, same asymptote, but now it's decay. So it looks like a horizontal reflection compared to what we had before. Well, with a logarithmic function, when you have a base between 0 and 1, again, same asymptote, same x-intercept, but now it'll appear like a vertical reflection compared to what we had before. And so, again, in general, for any exponential and any logarithmic function, like I've kind of mentioned before, the domain of an exponential function is all real numbers. The range is y is greater than 0, and there's an asymptote on the x-axis, so where y equals 0. For a logarithmic function, the domain is greater than 0. The range is all real numbers, and the asymptote is on the y-axis, or where x equals 0. OK, so what I want to start focusing on now is just understanding what a logarithm means if we just see the equation or see an expression with it. And anything written in logarithmic form, like I have right here, log base c of b equals a, can be written in exponential form. And so log base c of b equals a is equivalent to c to the power of a equals b. So let me draw your attention to a few things here. First of all, the base of your exponential function is the base of your logarithm, and vice versa. They're not just, they literally represent the exact same thing. Hence, it's log base b. Notice the input of my exponential expression or equation is the output of my logarithmic equation. And the output of my exponential equation is the input of my logarithmic equation. These two, again, are equivalent. They mean the same thing. One's not better than the other. One probably looks simpler to you because it's, exponential equations you've been seeing for years, even before you learned about an exponential function. But they represent the same thing. They're perfectly equivalent. So anytime you see an exponential equation, you can think of it in logarithmic form and vice versa. That's it. I have a little note here. Log base 10 is a very commonly used logarithm in sciences, not so much in a calculus course actually, but in sciences. And so log base 10 we call the common logarithm, and we don't tend to write the base. So anytime you see log base 10, we usually just write it as just log of x, or log of whatever. So if you don't see a base beside a logarithm, it's what we call the common logarithm, and it's log base 10, the inverse of 10 to the power of x. And if you've used a logarithm in like a chemistry class for pH, and we'll look at pH a little bit in this course, you're working with log base 10. That's it. This is a pre-calculus course, and in a calculus course, log base 10 is actually not that useful. There's another logarithm that's more useful, and we'll get to it at a later time. That's it. Let's evaluate each of these, or simplify each of these, without using a calculator, really to understand what these mean. Okay, so log base 4 of 0.25, what does that equal? Well, when you think about what this means, and in exponential form, it's probably a lot easier to understand. This means 4 to the power of something equals 0.25. So that's what that means. And so when you're trying to think about what log base 4 of 0.25 means, you're also in the same way you're trying to think about this. 4 to the power of what equals 0.25? Well, if I write 0.25 as a fraction, it probably makes it more obvious. And 4 to the power of what equals 1 over 4? Well, remember I work with negative exponents. A negative exponent means dividing. And so a power of negative 1 means you're dividing once. And so you're dividing by 4 once. That's the same as multiplying by a quarter. And so log base 4 of 0.25 equals negative 1. And so the log of 100, which means log base 10 of 100. All right, means then 10 to the power of what equals 100? Well, whatever goes there is what this equals. And so I can see this equals 2. And on any scientific calculator, if you type in the log of 100, hit that, use that log button, it should say 2 because you were asking it to find the log base 10 of 100. All right. Next, log base c of c to the power of a. Okay, so what does this mean? Well, this means I have c to the power of something, that's what we're trying to figure out, will equal c to the power of a. Well, once I write it like this, it should be pretty obvious what that something has to be. C to the power of what must equal c to the power of a? Well, that blank there must be just a. Now, notice, this is not a coincidence. I have a logarithm of base c, and inside it, I have an exponential function of base c. Those are inverses of each other, right? By the definition of a logarithmic function, it is the inverse of an exponential function. And these are inverses of one another. And what happens when you put an inverse inside put one function inside its inverse? They undo each other. They cancel each other out. And notice all you're left with is the a. So again, if I ask you what log base, 8 of 8 to the power of 12 is, hope you just realize those are going to cancel out. And so the answer must be 12. And the idea is the exact same as if I asked you, what is 8 to the power of 34, but then take the 34th root. Hopefully you realize I don't really need to calculate anything. These are going to cancel each other out. The answer must just be 8. And so with that said, let's look at this. Log base c of 1. So what does this mean? This means c to the power of something equals 1. So what's that something? Well, remember, anything to the power of 0 equals 1. So this must be 0, right? Anything to the power of 0 except for 0. But remember, you can't have a base of 0 anyways for an exponential and therefore a logarithmic function. So if we're dealing with logarithms, we're never dealing with a base of 0 anyways. And so anything to the power of 0 always equals 1. Last two examples before we get to a final problem. Oh, I forgot to erase that. Gave away something. Anyways, log base c of 0 means c to the power of something equals 0. And this is not possible. I can't take a number unless it's 0, but again, I can't have a base of 0. C can't equal 0. I can't take a number, raise it to the power of anything, and get nothing. I can get really close to nothing. I can get really close to 0, but I can't actually get 0, so this is not possible. And if you replace, if you tried something similar on a calculator, it would give you an error. And lastly, you may have seen I already had the answer to this. This is also not possible. And hopefully it becomes fairly clear if we think about what this means in exponential form. This means 1 to the power of something equals 2. I can't take 1 and repeatedly multiply or repeatedly divide. Remember, negative exponents is repeated division. And I can't do that, any combination like that with 1 and get 2. 1 times itself is always going to equal 1. 1 divided by itself is always going to equal 1. It's never going to equal 2. So this is not possible. And maybe I should say that for this one here. Draw a line through there. All right. So there's various logarithmic scales you need to be familiar with. The first of which we're talking about here, which is the Richter scale, which I'm sure you've heard about. It's a way of measuring the intensity of an earthquake. And it is a logarithmic scale, which means to calculate the measurement, you need to at some point apply a logarithm of base 10. And so this is a math class, though, not a seismology class. So most of what I'm interested in fact, entirely all that I'm interested in a question like this is that you understand the impact of the logarithm and how to work with it. I don't really care about, a lot of the details of like what I say right here, for example, which is the Richter scale is a scale for measuring the intensity of earthquakes. That's important by comparing the amplitude of an earthquake shaking to that of a standard level of shaking, defined as magnitude 0. That last part doesn't really matter too much for what we're going to do here. It is a logarithmic scale of base 10 as follows. So the magnitude, right, this is the magnitude of the earthquake, is found by finding the log. There's no base there, so that means log base 10 of A, where A is the amplitude of the earthquake, although as we'll see in a bit, that number doesn't really matter, divided by A naught, which is the amplitude of what we call a magnitude 0 earthquake, which is an arbitrary shaking that I presume Richter came up with for this scale. But again, as we'll see, that A divided by A naught, those individual values will never actually be important to me. What will be important to me is the quotient of everything inside those brackets. First, though, let me show you what I mean, how to calculate this, for example. For example, if a seismometer shows that there's an earthquake that is 500 times more powerful than the magnitude 0 earthquake. Okay, well, we'd find the magnitude of the earthquake by first realizing the earthquake we're looking at is 500 times that A naught. It's literally as it highlighted in blue, is 500 times more powerful than A naught, divided by A naught. But again, notice these A naughts actually kind of cancel out. So in the end, all that really matters is that this earthquake was 500 times more powerful than A naught. And so all that really matters is the log of 500. Log base 10 of 500, which is about 2.7 using a calculator. And again, that means 2 to the power of 2.7 is approximately 500. Right? That's what the calculator is kind of telling us. Okay, so if there was an earthquake that was 500 times more powerful than this magnitude 0 earthquake that I believe was Richter, hence the name, the Richter scale, kind of set up this measurement system, that earthquake would be 2.7 on the Richter scale, which I will say you wouldn't even feel. If as you're watching this, there was a magnitude 2.7 earthquake taking place right around you, you probably wouldn't feel a thing. And that's 500 times more powerful than A naught. So that kind of shows you just how little shaking A naught is. Okay, this magnitude 0 earthquake. With that said, here's the actual question I want us to look at. So what I'm really here is comparing two actual earthquakes. One in Japan in 2011, that was 9.03 on the Richter scale. And it was one of the most powerful earthquakes in modern history. A year later in Canada, in Haida Gwaii, there was a 7.7 magnitude earthquake on the Richter scale. And that was the most powerful earthquake in Canada for a long time. So the question is, okay, it's pretty clear that the Japanese earthquake was more powerful than the Canadian earthquake. How many times more powerful? And when you're dealing with logarithmic scales, a little change in the magnitude, we say here, can make a very big change in what it actually represents. And so it's hard to tell how many times more powerful that earthquake is. It looks like it may just be a little bit more powerful because 9.03 is a little bit more than 7.7. But we'll see it's actually considerably more powerful. First, let's write down again what this was. The magnitude of an earthquake is the log of the amplitude divided by A naught. But like I'm going to keep saying, it's all of this in here that's going to matter, not those individual values. So if I look at Japan, we know the magnitude. It was 9.03. As for what goes in here, I don't know. But honestly, I don't care about A divided by A naught. I just care about all of it together. I care about really how many times more powerful was the Japanese earthquake compared to this A naught. That's what I really care about. And so I'm just going to call this, put the variable J here for Japan. And that J there represents how many times more powerful the Japanese earthquake was compared to A naught. I don't really care about the individual values of those two. And so similarly for the Canadian earthquake in Haida Gwaii, we know the magnitude, 7.7. We know it's the log of, again, this A over A naught, but all I really care about is the quotient of all of that together. And so I need to figure out how many times bigger is this number compared to this number. Well, let's figure out those numbers. And to do that, let's get these out of logarithmic form, because what we have here are two equations in logarithmic form. And if I think about what these mean in exponential form, it's probably pretty easy to compare these. So what does 9.03 equals a log of j look like in exponential form? It's 10, because again, this is log base 10. It's 10 to the power of 9.03 equals j. Notice the input of the logarithm became the output of my j looks like a 3. Let me try that again. Take 2. The input of my logarithm is the output of my exponential equation. And honestly, 10 to the power of 9.03, I could just type into my calculator right now. I'm not going to. It's some big number. But that'll tell me how many times more powerful the Japanese earthquake was compared to this A naught earthquake. Well, for the Canadian earthquake, again, this log is log base 10. So this means 10 to the power of 7.7 equals C. And so now I can just take this value here, divide by this value here to tell me how much larger it was. That's what the question is asking, how many times more powerful. And so in the end now, I just want to compare these and take my larger, which is 10 to the 9.03, and divide by the smaller 10.7, 10 to the power of 7.7. And that will tell me how many times more powerful the Japanese earthquake was. That's it. I could go to my calculator. 10 to the 9.03 is going to be in the billions. That's it. I am dividing two powers to the exact same base. So I also can just use my exponent laws and realize this is going to be the same as 10 to the power of 9.03 minus 7.7. Or I believe that's 3.3. I don't want to make a silly mistake. Sorry, 1.33. What am I doing? No. What am I? Hold on. Yeah. 1.33. Okay. And so again, 10 to the power of 1.33 is just if I simplify that down. That's it. It's not wrong to go to a calculator, although I generally try to avoid dealing with really big numbers. If you go 10 to the power of 1.33, you get about 21.3. So that means the Japanese earthquake was 21.3, about times more powerful than the Canadian earthquake. More than 21 times more powerful, more than 21 times more energy released compared to the Canadian earthquake, even though the difference of the magnitude was only 9 compared to 7.7. And notice, though, in the end, the only calculation that I really needed to do was getting it right at the end here. If I wanted to decimalize, if I wanted to evaluate this, yeah, I wanted a calculator. But really, this right here just required me going 9.03 minus 7.7. I never had to deal with these gigantic numbers. And all logarithmic scales are like this, where a slight change in the number can make a profound difference in what it means. And the point of logarithmic scales is they can show a huge range of possibilities without a huge range of numbers. The difference between a magnitude 9 earthquake and a magnitude 1 earthquake is going to be 100 million times more powerful. A magnitude 9 earthquake is 100 million times more powerful than a magnitude 1 earthquake. And by using a logarithmic scale, though, we don't have to have, big earthquakes don't have to have these enormous numbers in terms of measuring the magnitude. But it's also deceiving. It's deceiving to realize that how much more powerful a 9 earthquake is compared to one that's almost 8. With that said, though, we'll look at just a few of these scales in this course, but that's it for now.